Hello, welcome to my presentation entitled Investigating the Optimal Ratio Between Drug and Co-Forma and Co-Amorphous Systems. So most drugs today, low molecular weight drugs anyway, show a too low aqueous solubility. So they are belonging to class 2 or 4 of the biopharmaceutics classification system. And one way of overcoming this too low aqueous solubility is by converting a crystalline form of a drug to an amorphous form. So in a crystal, we have a three-dimensional long-range order with respect to orientation and position of the drug molecules. As such, we have a low energetic state, and that is also leading to a low solubility. But it is thermodynamically a stable state. If we are converting a crystalline drug to an amorphous form, we are getting rid of long-range order in these systems in all dimensions. So there's no positional or orientational long-range order in these systems. There may be still short-range order, and I come back to that a little later. And this higher disordered state leads to a higher energy. A higher energy state leads also to a higher apparent solubility, but this comes at the cost of thermodynamic instability. So if we're looking at this from a thermodynamic viewpoint, and we're looking at, for instance, enthalpy or entropy, then if we heat up a crystalline material, these properties change gradually until we come to the melting point where heat capacity gets infinite, and we get the transition from the solid crystalline state to the melt state. If we're not cooling down the melt again, we would get crystallization back to the crystalline solid state. If we, however, melt fast enough, we can overrun this recrystallization, and we come into the area of the supercooled melt. In this area here, we still have a liquid system, but with increasing viscosity as we lower the temperature, we are in a much higher energetic state compared to the equilibrium state, which would be again the crystalline state. And this changes now as we cool the system further until at some certain temperature, the slope of this change will change, and we're coming into the area of the amorphous solid. So this change in slope in thermodynamic properties that we are observing at some temperature is the well-known glass transition temperature. And below the glass transition temperature, now our amorphous solid is really a solid, but it retains a high degree of disorder. We have no long-range order in any of the dimensions. We are also in a high energy state, as you can see here by this line being higher than that line. And this high energy disordered state then is the reason for the higher solubility of an amorphous solid compared to the respective crystalline state. And it's also the reason why these amorphous systems are thermodynamically unstable. So they will crystallize after some time back to the crystalline state. Some drugs, however, can be converted into an amorphous form and are stable enough for the shelf life of the intended dosage form. So here are 4 examples of drugs that are actually marketed, being indeed marketed as amorphous drug themselves. So here the drug alone is the amorphous form. For most drugs, however, such an amorphization would not be stable enough, so the drug would crystallize too quickly in order to be useful for increasing solubility, for example, of the drug in the intended dosage form. And in those cases, most often used formulation approach is to not use the amorphous drug by itself, but rather convert it into an amorphous solid dispersion with the help of an amorphous polymer. So the polymer is amorphous and it can't crystallize because simply it's too big as a the polymer molecules are too big, they cannot crystallize. And now it can act as a solvent for drug molecules into the polymeric matrix. So if the drug is molecularly dispersed in the polymer, we call that an amorphous solid dispersion. So we can treat it like a normal solution, meaning that at some point we can add too much drug. So the drug now becomes supersaturated in the polymer. This is, of course, different at different temperatures. And that would be a supersaturated amorphous solid dispersion. And now the excess drug again could crystallize over time. But if we are staying below the solubility limit of the drug in the polymer at, for example, the storage temperature, then that drug cannot crystallize at all. So by determining the drug in polymer solubility as a function of temperature, at the same time by determining the glass transition temperature, we can establish the phase diagram of drug polymer mixtures with respect to temperature. And we are having this zone 1 here where we are below the TG, so we're in the solid state, and we are left of the solubility curve. That means we are subsaturated with respect to the drug concentration in the polymer. Then we have a stable amorphous solid dispersion. So this drug in this polymer at this temperature cannot crystallize. And that also gives us a good rational starting point to develop the ideal ratio of drug to polymer. If we want to be safe that this drug cannot crystallize, we have to stay left of the solubility curve. And if we go above that, if we have too high drug concentration, we are entering the metastable zone. So now we have perhaps still a stable system with respect to the shelf life of the amorphous solid dispersion in a tablet formulation, for example. But we are now in a zone of kinetic stabilization, meaning that we have to check and test whether the drug will be stable and not crystallize in the shelf life of the product. So there is a clear path to find an ideal and useful ratio of drug to polymer. However, amorphous solid dispersions are a good solution to the amorphization problem of many drugs, but they also suffer from some disadvantages. So many of the polymers have a very high hygroscopicity, and oftentimes the drug solubility in the polymer can be very low, meaning that we need to use a lot of polymer in order to make an amorphous solid dispersion. So alternative approaches to amorphous solid dispersions are still useful to be investigated. And one such alternative are the so-called co-amorphous systems. A co-amorphous system consists of two low molecular weight, initially crystalline materials that upon co-amorphization are mixed at the molecular level to form a single amorphous phase. So rather than having a dissolution of the drug in the polymer, where the drug is the solute and the polymer is the solvent, here we oftentimes are looking at interactions between drug and co-forma, and that can lead to short-range molecular order, and that can bring about a co-amorphization, especially if these binary systems here, these heterodimers, have nowhere to go. So if there's no corresponding co-crystal for these systems, they could crystallize too, and that could lead to a higher amorphous stability compared to the drug alone in the amorphous form or the co-former alone in the amorphous form. So if we start with a very old example, then we can look at drug-drug combinations. Here we have the drug naproxen and the drug cimetidine. The drug naproxen is a class 2 drug. Cimetidine actually is a class 3 drug. So both of these drugs can be converted or can be attempted to be converted into an amorphous form on their own. And if we do that, we'll see that cimetidine, for example, here in the crystalline form, can be converted, for example, by ball milling into an amorphous form. They're characterized by the halo of the XRPD diffractogram. For naproxen, this is not successful because naproxen in its own right in the amorphous form has a very low glass transition temperature. So maybe intermediately during the milling we get amorphization, but because the temperature during milling will be too high, we come to the supercooled melt state of this amorphous form of the drug and we get crystallization. This is not the case for cimetidine, and of course it is depending on the ball milling conditions that one uses. But by and large we can say naproxen alone we cannot convert to an amorphous form by milling. Cimetidine we can. But now what happens if we are using different molar ratios of these two drugs? So here we have the 1:2, 1:1, and 2:1 molar ratios of naproxen and cimetidine. And we can see that now in all cases, after the same milling conditions, we are arriving at an amorphous system, and it has different glass transition temperatures, mainly depending on the TG of the higher TG component cimetidine. So the more naproxen we have, the lower is the glass transition temperature. But initially the 1:2, 1:1, and 2:1 molar ratios are all amorphous. If then, on the other hand, we wait, and here, for example, we did a 60-day storage study at dry conditions, we see that in the 1:2 and 2:1 system, the excess component starts to crystallize. So in this case, this would be cimetidine, and this is a peak here coming from cimetidine, and here it would be the naproxene, and here we can see the naproxene peaks coming at different storage conditions differently fast. However, the 1:1 molar ratio was stable. It was the most stable at all storage conditions for the longest time. And that led us to believe that it is not the highest TG that brings about the stable amorphous form, but that it is a molecular interaction between cimetidine and naproxene and cimetidine. So the 1:1 molar ratio appeared to be the logical choice, and that has led to many more co-amorphous system investigations in which different molar ratios were used. And perhaps to believe that a 1:1 molar system, if there is a 1:1 interaction forming a heterodimer in the amorphous form, is the optimal ratio of drug to co-former. But this may not necessarily be so, and in fact, in many cases, it isn't. So how can we find out the optimal ratio of drug to co-former in co-amorphous systems? Let's first have a look at eutectic systems. So here we have the drug indomethacin together with the drug naproxene. We have just seen this example. Here's another example, celecoxib and paracetamol. And if we are mixing these two drugs, or if we're mixing two of these drugs at different ratios, then these are molar ratios. No, these are percentages. Then we can see that starting with the crystalline mixture, we get a typical eutectic sort of behavior of these two components. So we get one endothermic event at some temperature, and then a second endothermic event that comes at various temperatures depending on the binary mixture. And this we can see here indicated by the little black arrows. And here's the same for the other system. So this is paracetamol, celecoxib. Again, we can see one endothermic event here, and then a second endothermic event that comes at different temperatures depending on the mixing ratio of the two drugs. And if we are using this thermal data, we can determine the eutectic mixture of the two drugs. So in case of naproxene, indomethacin, this would be around about 40 mole% of indomethacin and naproxene, 60 then accordingly. That would be the eutectic mixture where we only see one thermal event in the DSC. And for the celecoxib paracetamol system, this eutectic mixture would be around about 50%. If we are now preparing amorphous samples for these various systems, or make binary systems here by melting and quench cooling, we see that some of them cannot be made amorphous even if we cool very fast. Other ratios can be made amorphous. And this is depending, of course, on the system, but it will also to some extent depend on the cooling rate that you're using. So the systems that we could make amorphous now, we can look at their glass transition temperatures, and then we see that the glass transition temperatures either decrease or increase in TG with the increasing or decreasing drug concentration. So here we have a higher and higher glass transition temperature if we have more and more indomethacin. Here we have a higher and higher glass transition temperature if we have more and more celecoxib. So this seems quite monotonous, and we cannot really discern a optimal ratio of the two drugs to make a co-amorphous form. However, when we now put these different systems on stability, then after some time, we see that we get crystallization of either one or the other component in our system. So we get visible indomethacin peaks at high indomethacin concentrations and visible naproxene peaks at high naproxene concentrations. At around about 40 mole% of indomethacin to naproxene, the system is the most stable. So it is at 40 mole%, not at 50. At 50, we already see some peaks. 50-50 would be 1:1 molar ratio, but here it was at 40-60. So if we plot the stabilities as a function of the molar ratio of the two components for our systems, naproxene, indomethacin, and celecoxib paracetamol, we get this kind of stability stabilities for the various systems. And if we overlay this now with the eutectic behavior of the system, we see that the co-amorphous system at the ratio of the eutectic system for the two crystalline components also has the highest stability. So here the 60-40%, in the case of silicooxyparacetamol, that is the 50-50%, but it's we believe not because we have a strict one-to-one heterodimer formation, but the eutectic mixture has this concentration, and that is then leading to a co-amorphous form that also has the highest stability. So for systems that can form eutectic mixtures, the eutectic mixture itself, the ratio of drug to other component in the eutectic system, is a good starting point to finding the ideal ratio also in a co-amorphous system. These were weak interactions. Many co-amorphous forms are actually ionic, so they are amorphous salts. So we can look at the ratio of drug to co-forma also for systems that have ionic interactions. And here, initially anyway, we thought that it stands to reason that the stoichiometric ratio between acid and base forming the co-amorphous salt would be the ideal ratio. So we investigated this with the model drug carvedilol, and then various different organic acids, namely benzoic acid, malic acid, and citric acid. And initially, we were making them at various ratios, 4:1 to 1:4. These are molar ratios. In this case, the sample preparation method was spray drying. And if we do that, in practically all cases, initially we get a co-amorphous system. Only the carvedilol benzoic acid 1:4 system did show some crystallinity of the benzoic acid. All the other systems were amorphous after spray drying. And if we look at the glass transition temperature of these systems, then we see that we get different glass transition temperatures depending on the mixing ratio of drug to co-forma. So in our case of carvedilol to the organic acid. But interestingly, for example, for the carvedilol benzoic acid system, the highest glass transition was not at the stoichiometric ratio of drug to organic acid of 1:1. That would be complete salt formation. And we thought that, okay, this should have the highest glass transition temperature. And then if we have an excess of one or the other component, because it having a lower glass transition temperature, it will lower the overall TG. But this is not so, because the carvedilol benzoic acid 1.5:1 system had a higher glass transition than the 1:1 system. And so it's not the stoichiometric ratio between drug and polymer, drug and organic acid that is decisive here. On the other hand, for the malic acid, where we have two carboxylic acid groups, we get the highest TG at the 2:1 ratio. And then again, at the citric acid, where we have three carboxylic acid groups, the highest glass transition temperature was again at the 2:1 ratio. So the highest TG values were at ratios that, at least in case of benzoic acid and citric acid, were not expected. If we now taking these samples and put them on stability, we do see that we get the highest stability at the ratio that also had the highest glass transition temperature. At least for benzoic acid, we can say that because we waited long enough. For the other systems, the amorphous stability for other ratios was also very high, and we stopped the study after 6 months at 40 degrees. But suffice to say that the highest glass transition temperature leads to a high stability, and that may not be the stoichiometric ratio in a co-amorphous salt. Now we extend this study to look at the drug with amino acids. Here we again use our drug carvedilol, and now we are taking one amino acid as co-former, that is aspartic acid, that can form a salt with carvedilol, and one that is tryptophan that cannot strongly interact with carvedilol, but perhaps can have weaker interactions, hydrogen bonding or bi-stacking or so with the drug. So let's see what happened there. If we're looking at the strong interacting system first, we can calculate the theoretical TG on the basis of no ionic interactions. based on the glass transition temperatures of the pure drug and of the pure amino acid. And that can be then done according to the Gordon-Taylor equation. And we get this line here, which is the theoretical TG line. If we are now making our systems and we are measuring the TGs experimentally, we get a strong deviation from the from the theoretical TG line, meaning that we do have strong interactions between the drug and the co-former. However, the maximum deviation from theory was again not at the 1:1 molar ratio, but at the 1:1.5 molar ratio. That is interesting. And if we are looking at this even more carefully, we can fit functions to the low drug concentrations and to the high drug concentrations, and we get this crossover point roughly at 1:1.5 drug to amino acid. And if we're looking at the respective FTIR data, and we're doing a principal component analysis on the FTIR data of our co-amorphous systems, then for starters, we see that the first principal component almost looks like the spectrum of amorphous cavity LOL. So the first principal component separates the samples according to varying molar ratios of drug to co-former. But the second principal component has maxima that are corresponding to some group vibrations that might well be included in the interaction between the drug and the co-former, for example, the carboxylic acid group of the aspartic acid. And so if we are plotting now our samples in a PCA score plot with respect to the first and second principal component from 2:1 to 1:3 systems, we are seeing that we get a maximum for the second principal component at the 1:1.5 molar ratio, again indicating that it is not the 1:1 molar ratio that has the highest stability or is the ideal ratio of drug to co-former, but in this case, again, the 1:1.5. So the amorphous salt forms, but then excess aspartic acid acts as a co-former now to the amorphous salt, and that leads to a co-amorphous system at 1:1.5 with the highest stability. Or does it? Yes, it has. Here we have the different ratios of drug to co-former stored at quite high temperatures, and here the 1:1.5 system at 65 degrees storage temperature at the highest stability. So this stability study ran for 2 months, and the 1:1.5 system had the highest stability. Now let's have a look at the same drug, but now a different amino acid. Now we are using tryptophan. It cannot form an amorphous salt with the drug, but it can interact maybe with weaker interactions. So let's say it's a non-strong interacting amino acid for this particular drug. And here we again look at the thermal behavior of various co-amorphous systems. Initially, you can make them amorphous for some time anyway, at many ratios. And here we are determining the thermal behavior using dynamic mechanical analysis, not DSC, but DMA. And we get this large peak here in the tan delta, and that corresponds to the glass transition temperature of our co-amorphous system. But it's not the only thing we see. If we zoom in here in this temperature region, we see a second transition here, and that is the beta relaxation of the co-amorphous system. So we have the alpha transition here, the glass transition temperature, and here we have the beta relaxation that it has not to do with cooperative motions as in case of the glass transition, but individual molecular motions in this case. So this beta relaxation here can be determined by DMA. It cannot be determined by DSC. We don't see it there, but in the DMA, we can see it as well as the glass transition temperature. So if we are plotting the glass transition temperature as a function of the binary mixture, again in mole percent, we see that in these weakly interacting systems, we see hardly a deviation from theory. So there's very little in terms of interaction, and the experimental data points follow the theoretical glass transition temperatures closely. The absolute difference here we see in the DSC determined and the DMA determined glass transition temperatures is experimentally is due to the different experimental methods that we are using. Don't have time to go into details with that. Suffice to say that the TG in a DSC measurement is always lower than the TG that we see in a DMA measurement. But if we are using the 100% drug and 100% amino acid TG in either method, we get a theoretical glass transition temperature curve, and our experimental data follows that closely. So the TG alpha is not very useful to determine an ideal ratio, in this case of weak interactions. However, if we are looking at the beta relaxation, a different picture emerges. The beta relaxation temperature here for some systems remains hardly unchanged. Please note the very narrow temperature here on the y-axis, only going from 215 to 240 Kelvin. But at some point, we get a change in the beta relaxation temperature to another beta relaxation temperature. So we have similar TG beta values over large concentration ranges of the drug and the amino acid, and this implies that these transitions originate from an excess component. So here we actually measure the beta relaxation of the excess component tryptophan, and here we are measuring the beta relaxation of the excess component carvedilol. And if we are plotting these in a way like this, then we would assume that the optimal ratio between the co-former and the drug would be around about 40 mole% of drug. And indeed, if we are putting those different co-amorphous systems on stability, we see that at higher drug concentrations, we get drug crystallization, and at higher amino acid concentration, we get amino acid crystallization, but the highest stability was at the optimal ratio around about 40 mole%. So in conclusion of this presentation, I'd like to point out that in systems that can form eutectic mixtures, the eutectic ratio is a good starting point for finding the most stable co-amorphous systems. In systems with strong interactions, it is not necessarily the stoichiometric molar ratio of the strong interaction that leads to the most stable system. In systems with weak interactions, the beta relaxation values can be a good guide to find the most stable system. So current work going on in our group looks at other methods to determine the ideal ratio of drug to co-former for systems with weak interactions, because beta relaxation measurements are not easy. And I can already say that also with IR-based methods, we can find the ideal ratio in case of non-strong interacting systems. We are also currently looking into the ideal ratio if we store at non-dry conditions. So what happens to our ideal ratio that we have determined for dry storage conditions if moisture indeed is present? So I want you to stay tuned, and maybe next year at the second electronic conference, hopefully I can report about the results of these two ongoing investigations. Details to the papers that I have used in this presentation are listed here, and I want to thank our solid state research group, my collaborators, Associate Professor Corbinian Löbmann and Associate Professor Holger Rogans, then a lot of students here, and specifically data was taken from these students here, Wang Shi, Eric, and Jing Wen. So I want to thank them especially. And I also want to thank you for listening.